Now, in a lot of these problems, we're thinking about work done by a constant force. But what happens when the force is not constant and it's doing work? So let's say an object is displaced under the action of a force that varies with position. In that case, we can't just say work is equal to force times displacement because that force is changing every time step. This relationship only applies, as it's written here, when the force is constant in magnitude and in direction. But we can consider that our object undergoes a small displacement delta x over which the force is nearly constant. So then we have this situation here. This is exactly like what we did in lab with the spring lab that all of you just finished. So here we have a plot. We've got the force on the vertical axis that we're applying, and we've got our displacement on the horizontal axis. And you can see the force that we're applying varies over distance. So what we can do is, we can't just go ahead and use that equation, work is equal to force times displacement, because that force is changing every time step. But what you can do is get these little skinny areas in here and calculate the work that's done by just the work that's done as you move a small distance. So if we move a small distance, we can calculate the force that we're applying over that small distance that we moved. Then we can calculate the work that we do in that little time step. And then you can calculate the work that you do in subsequent little time steps as you're changing the force and you're moving through a displacement. And so what you end up having is a bunch of these little long skinny areas here that are each on their own equal to the force applied, which would be its height here of the area, times the distance over which you apply that force, which would be sort of the width of this long skinny rectangle here, okay? And so if you add up a bunch of these long skinny rectangles together, you get the total work that's done. So the work that we do on a system is equal to the area underneath a force versus displacement graph. Work done is equal to the area underneath a force versus displacement graph. So what you can do is you can break up these graphs into little sections, little tiny areas like what we just talked about, and then you could sum up all those little areas, and that would be your total work done. We did the same thing in lab where we had the spring and we were applying the force and measuring that variable force as we stretched the spring over different displacements. So again, the work done by a variable force. To find the work done by the variable force, you take the sum of all the area underneath this force versus displacement graph. Okay, so what we see here is the force magnitude F here versus displacement X of a needle in an epidural procedure as the needle moves through the tissue. And so you can see that the force increases linearly as the needle goes in, and then the force slows down, maybe it hits some tissue. And so there, in any case, is a variable amount of force that the needle is applying as it's moving through some displacement in the tissue. And in order to find the total work done, you can break this up into a bunch of little areas and sum up all of those little areas. So that's the area underneath our curve, which is equal to the work done by a variable force. Let's apply that idea to this graph right here of a variable force applied over a distance. We have a force on a block. This force is directed along the x-axis. We want to find the work done by moving our block from 0 to 8 meters. Okay, we don't have any friction. So we're moving our block. As we're moving it from 0 to 2 meters, our force is constant. Then as we move it from 0 to 4 meters, our force diminishes to 0. So here just a 0. So to find the work that we do to move our object from 0 to 4 meters, we find the area underneath the curve. And that area will be from 0 here, okay, up. So we find the area of this little chunk, and then we find the area of this little triangle. We add them together. That's the work that we do in moving our block from 0 to 4 meters. So that's a positive quantity for work. And then we come over here, and from 4 to 6 meters, there's no force applied, but we're still moving some displacement, moving some distance, so there's no work done. And then over here, okay, we're still moving from 6 to 8 meters along the x-axis, but now our force is negative. That means our force is opposite the direction of displacement. Okay, if our force is opposite the direction of displacement, then we're going to be doing negative work on the system. And so to find that value of work, we start here at our 0 axis, and we find this area of this little triangle right here. And this work is going to be negative because this force is applied opposite the direction of motion. So that's going to be a negative value for work. And you're going to find the area of that little triangle right here. So the total work would then be the sum of this rectangle plus this triangle minus the work that you do in this little triangle here. This work over here is negative because that force is applied opposite the direction of motion. So FD cosine theta is our work. So we apply the force. D is our displacement. If our force is opposite the direction of our displacement, then cosine of theta, theta would be 180 degrees. So cosine of 180 degrees is negative. That gives us a negative value for work, okay? So you're gonna add positive values for work over here by finding the areas underneath the curve between the 0 axis and that black line. And then over here, you're gonna subtract the work